This is the plate tectonics and earthquake activity, and there's two parts. First part is modeling the motion of plates at their boundaries. The second part is modeling earthquakes and how force builds up and motion happens. But before you do either of those parts, you could talk about how scientists came to understand the theory of plate tectonics. It's very new. When I was a kid, they didn't teach us that. It was not, it was around, but not everybody believed it. But now, essentially, all scientists believe plates move on the surface of the Earth. They're floating on the magma, and their motion is what makes earthquakes and volcanoes and mountains and mid-ocean ridges. And it explains all these things that were unexplainable before the understanding of plate tectonics. And so it's good to understand that, and you can see, you get a picture of the plates, the world's plates, and some are big and some are small, and there's not that many, and then there's certain boundaries, and you can see that we are, right here in California, we're right on the boundary of two plates, the Pacific plate and the North American plate. And so things are gonna happen, things are gonna move. And then another thing to show is very interesting is, oops, not touch screen. This is a picture, it's kind of a famous picture, is how you can show that this is for real. If you just plot all of the volcanoes and earthquakes in a certain amount of time all over the world, just put a dot, it's a black dot for an earthquake and a red dot for a volcano, you get a broad outline of the tectonic plates of the world. And so scientists have done that, and you can look at that and you can say, oh yeah, all these earthquakes and volcanoes in a ring of fire, that is defining the edge of the Pacific plate. And in other places of the world, it works the same way. So that's science in action. So then before you go to the first activity, you can talk just with your hands, get everybody to put their hands up and say, at a plate, at the boundary between two plates, there's three things that can happen. All right, it's very straightforward. One is they can move beside each other like that. That's called transverse boundary, transverse. That's what we've got here in California. It's been moving that way for millions of years. In fact, the Pinnacles, right down the street here, the Pinnacles has a bunch of very interesting mountains and peaks, and there's another one about over 100 miles to the south that's this other half of it, because it is sitting right on top of the San Andreas Fault, and the other half has moved south about 100 miles. So that's a transverse fault. Okay, so everybody does that. Transverse fault. Don't go like this. They don't go back and forth. They just go one way. Okay, and then another thing they can do is move apart. That's a divergent fault. And when they move apart, then the magma comes up from underneath. That happens at a mid-ocean ridge. The Atlantic mid-oceanic ridge is a mountain range on the bottom of the ocean that was formed when the magma came up as the plates spread apart. Okay, so that's a divergent fault. And the final fault is a convergent fault, and the two plates are pushing on each other. They're smashing each other, forces directly against each other. And in this case, you get a mountain. It builds up a mountain, either buckles like that, or one goes up on top of the other one. And it can be scraping off a bunch of stuff on the top and make a mountain of rubble together with a stronger mountain on the other side. And the other one goes down, subducted underneath, and it melts back into the magma. So you've got the one going up and the one going down. Okay, so those are the three possibilities. And of course, it's more complicated than that. Often you have more than one. You have pushing together. Right here in California, you have a little bit of subduction going on, and you've got the transverse happening as well. All right, so let's go to the hands-on activities. All right, once they got their plates with the crackers, then you model it one more time. You go one by one. So it's, oh, and everybody's got a little tray of water, not very much water. And you model it with your hands again, or you could model it with the crackers. The transverse is the first one we'll do. That's the one where one plate is going one way and the other's going the other way. They're pushing against each other a little bit, and one's going one way, one's going the other way. And you see, if you observe carefully, you can see there's all kinds of crud that comes off, all kinds of little pieces of rock and mineral, and we can find those things. You can go look on the side of the river. The Arroyo Seco is full of those things, where the two plates have been rubbing along beside each other. All right, so you put it in there, and then have them put it, so no peanut butter yet on the first one, just the two crackers. You're pushing against each other, and then notice that they usually go kind of jerky like that. Well, that's the way it works. A lot of plate boundaries, the pressure builds over the decades, centuries, millennia, and then bam, it moves. That's an earthquake. And if it moves a lot, it's a big earthquake. If it moves a little bit, it's a little earthquake. So let them make a bunch of little earthquakes. Just goes one way. It doesn't go like this. You don't want to do this. It just moves in one direction. All right, so that's transverse. That's the one that's right here in California. All right, and then we got the second one, which is divergent. Then you need the peanut butter. So you get out a little bit of peanut butter. This is enough peanut butter for about 4 years of this project, by the way. And put a big old blob of it right down in the middle of everybody's plate. And then you put the two crackers right on top of it, right close together. So you got two plates sitting on top of the magma. The peanut butter's the magma. And now here they're diverging. So you're gonna pull them apart and keep pushing down, because gravity's always pulling down. So as they come apart and it goes down, the peanut butter comes up, the magma comes up and makes, you can see, makes a little bit of a bulge, so almost like a little mountain. Well, that's the mid-Atlantic ridge. You can find that along the plate lines at the bottom of the ocean where the magma has come up and made a mountain. That was one of the final evidence that was found, pieces of evidence that was found that proved or showed that these plates are moving. Because if you go look at all that land down underneath the ocean, the stuff that's further away from the boundary is older. The youngest stuff is the stuff right in the middle, because it was the stuff that came up most recently. All right, so that's your divergent. All right, and then if they break a cracker, it's no problem. If they break a cracker, just give them another cracker. So far, mine haven't broken yet. So then you're gonna take one cracker and put it in the water for the final one, the convergent. Convergent, you put it in the water and you hold it there, I don't know, 5 seconds, 10 seconds maybe. And then you put it right back down there. And now instead of pulling apart with the divergent, you're pushing together. This is the convergent, and this is a mountain making process. So you push it together and whoa, let one of them ride up over on top of the other one, and there you have it. It's the Himalaya. Himalaya, you could see the Himalaya rose up because the one rock was softer and it rode up on top of the other one. This is all quite complicated at the real plate boundaries. It depends on the type of rock, the thickness of the plate, the density of the plate, the amount of heat below the plate. It's all very complicated, but more or less, that's what's happening. The two plates are coming together and one is riding up, and they're both kind of buckling, and that's building mountains. A lot of mountain ranges in the world were built that way. The tallest mountain range, the Himalayas, is currently being built that way. Every year it rises by a decimeter or 2 decimeters from this exact force between the Eurasian plate and the Indian plate that are jamming together there. All right, so that's it. After that, it's time to eat it. All right, for the earthquake activity, you've got a little base sheet here, folder, and a bunch of rubber bands. So you put together, let's see, how many was it? It's 10 rubber bands. You put all 10 rubber bands together. And this is one of the most useful knots. You gotta make sure all the kids know how to make this knot. All right, and then put it through the hole. The same knot. And you have that on one side, and on the other side you have the pencil. And again, you use the same knot. Now, the way to do it is with 2 fingers. 2 fingers going through like this, coming apart, bending down, back together, and you peel it off. You've got your little hole. Put the pencil through, and there it is. You could use a different kind of knot also, but that one's very useful. Now, before you start pulling, you gotta put some weight on there. So we've got these books here. Let's see if that's the right weight. And then you gotta mark it. You get the ruler, and you gotta get these little stickers. Because the stickers, every group needs at least 2 stickers. And I put 1 sticker right on the front of the little sheet that's gonna be moving in the earthquake. And another one right where the rubber band is. Slack, not tight at all. Right where the rubber bands come to, because that's where you're going to start rolling it each time. And then the ruler is going to be used to measure how many centimeters it moves. So you're going to measure from that tab over to wherever this thing stopped moving. All right, and then we use the extremely precise scientific method of twisting the pencil like this and counting how many twists it is. All right. So it doesn't matter how far you twist. The important thing is it's the same one every time. So each group is going to choose their twister, and it's got to be the same twister, because that's our unit. It's called an informal unit, a non-standard unit, and those are just fine as long as you're not comparing your data with somebody else's. So here we're just comparing our data with ourselves. We're going to use this non-standard unit of a twist. All right, so I'm just going to start twisting and counting and see when it moves. $38 twists. Okay, now I'm going to measure how far it slid. And then it slid 16 centimeters from the tab all the way to here. 16 centimeters. Now I've got my little table already. That's the first surface, is the tabletop here. And it moves 16 centimeters, and I pulled on it 38, or I twisted it 38 times. All right, so the group will have their data to take one by one. They should all be taking it, but maybe just one person can write it down, and then later they can copy off of that person's. All right, so then you set it up again, and be sure you're twisting from the same part. And you notice I wasn't twisting, I wasn't getting closer as I went, and I wasn't getting further either. I was staying right at this tab here. Okay, so now I'm gonna do it again and see what happens. 29. 29 times, and it moved much less. That's pretty interesting. It moved 6, only 6. All right, so that's 6 centimeters, 29 times. Okay, so now we can start thinking about what's going on. Why would it move less? Why would it start moving at less twists? It's all very interesting. You want to do it at least 6 times. You could do it more times if you want. And then you could average the data if you want to go through that with the students, how to add it up, divide by 6 to find out what the average is. But you can also just sort of look at the patterns that you see as you analyze the data. I'll do it one more time. 1, 2, 3, 4, 5, 6, 7, 28 times, and now it moved to 17 and a half centimeters. Yeah, 17 and a half. And I twisted it 28 times. So that's how it works. You do that all the way till you've got 6 pieces of data for this surface, and then you could go find another surface. Do it on the floor, on a piece of cardboard, on a carpet, outside on the cement or the asphalt or a piece of wood, just so that there's something different that it's sitting on. And you can also change the weight. You take off some of the books so that it's a different weight. And then you do it again. And you look at all this stuff and you look for patterns. And one of the patterns that you can see, or the lack of pattern, is that there's a lot of pretty arbitrary numbers. You have no idea when that thing is gonna break away. You have, it's between, whatever, right now mine are between 28 and 38 twists is when it starts to move. And then the amount that it moves is between 6 and 17 and a half. And that's kind of an indication of the challenge the scientists have predicting earthquakes and then predicting how bad the earthquake will be. We're adding force. When we twist this, you add a little bit of force every time you twist it. And that's just like the tectonic plates slowly building up force, building up pressure against each other, not moving over the years, decades, centuries. And then finally, they move. And nobody knows when they're gonna move. You're just making an estimate. You can look at the last time they moved and the last time before that. Scientists could do that. They can see at what point they moved. But then the next time, it's unclear. You can just have a wide range of possibilities. And so that's the challenge that we have. It depends on a lot of things. It depends on the kind of rock, the type, the minerals that are in there, how densely they're packed together, and how thick the plate is. It depends on a whole bunch of different things. All right, so the goal is for the kids to do this, take data, that's in the standards, and analyze the data, communicate the data. You can have them go around the room and say what they got in a sort of a summary of the data that they were taking, and then just to get this idea that an earthquake is very difficult to predict. We can't do it yet. All right, have fun.